today is really going to be the start of calculus. Now, limits, that is an important stepping stone to reaching calculus, these ideas of calculus. Welcome. And all of the, bless you, and all the prerequisites from your pre-calculus class, all of those are relevant as well. But it was really at this point that you had this man named Isaac Newton that realized the math that he needed to prove his laws of motion did not exist. And so the idea is, you know, if you're trying to explain why it is, for example, that the earth indefinitely goes around the sun, well, why is that? Why don't we have, why doesn't the earth just fly out into space? Or why doesn't the earth fall into the sun? There's this perfect balance going on between the forward velocity of earth and the gravitational pull into the sun. There's this perfect balance between those two forces. Now, those two forces are instantaneous. What has happened? We're not looking at an average. Let's look at the average. What happens if we calculate the average? What is the average? What's my average speed? Let's calculate my velocity. What is the velocity in 1 year? What is the velocity in 1 year? In 1 year, when the earth travels all the way around the sun, what's my velocity? Velocity is, what velocity specifically is, if we're looking at that, the average velocity over time. Now let's consider the velocity that it takes to drive down to St. George. Let's say that my average velocity is 60 miles per hour. Now the cool thing with velocity is a velocity is not just a magnitude. Velocity is also a direction. Velocity is a vector. Vector is calculated. A vector is a mathematical quantity calculated by, there's two pieces to a vector. Direction and magnitude. We have both of those. Now, when it comes to speed, we just have a magnitude. Speed is just a magnitude. It's just a quantity. There is no direction to a speed. When it comes to a velocity, there is a direction as well. Now, if I drive down to St. George, let's say that my average velocity is 60 miles per hour. If I drive back going the same speed, what's my average velocity?
60 miles per hour, but the direction is the opposite.
Yeah, so it'll be negative 60 miles per hour. So if I drive down to St. George and I come back to my home, what is my average velocity for that whole time period? Zero. It's zero. So what's my average velocity from this point right here all the way around the sun in 1 year? My velocity is zero. Now, it is true that we are part of the Milky Way galaxy. And so even though the Earth goes around the sun is going around the Milky Way galaxy as well. So there is still some extra speed calculated into there. We normally don't calculate that at all because we don't really know. Actually, we may know based upon the distance away from the center of the galaxy and what our speed is, but we don't really typically calculate that into it. And certainly Isaac Newton didn't do that as well. So he's trying, if he wants to show this perfect balance between our velocity and the vector pulling the earth into the sun, we need to calculate instantaneous quantities. We need to figure out things that are instantaneous. So I'm going to go back. I'm going to get rid of all this mess here. So really, this is where Isaac Newton first stumbled on that we don't have the math that we need to prove his laws of motion didn't exist. Do you guys remember what his laws of motion are? The first one is, for every action there is. Yeah, and the other one is a body in motion. Unless acted upon by another force. Yes, okay. So And then, of course, the further you get into calculus, the more you're going to realize how brilliant Isaac Newton was, because there's a lot of different things that come up regarding Isaac Newton besides just those 3 laws of motion.
Repeat the definition for vector.
A vector, we're not doing vectors at all in this class, but a vector in general, a vector has 2 values that are assigned to it. One is some type of magnitude, some type of quantity, if you will. And the other one is some type of direction. There's certain things that are vectors, like a velocity is a vector. It has a direction and a quantity assigned to it. You also have gravity. Is gravity a vector?
Yeah.
All right. The vector, our gravity for Earth, the vector is pointed in what direction?
To the center of the earth.
Towards the center of the Earth. And then we have some quantity assigned to it. If you take physics, you're going to find what's the meters per second, right? Isn't it like 9.8 meters per second? Okay, so that's the quantity. The quantity is 9.8, but the direction is down for when you're looking at gravity. And then, but we have other things like, we have something called distance, but we also have something called displacement. Displacement is a distance, but it also has a direction. So if usually when we talk about a graph like this, a Cartesian grid, and this is our 0, 0 point right here, and this is really, if you think of a type of physics called kinematics. Have you ever heard of kinematics before? Kinematics, we're looking at something that's not 2-dimensional, but is 1-dimensional. We're going to look at something that is 1-dimensional. So if it's only 1-dimensional, all we can do is left or right. All we can go is left or right. That is a 1-dimensional object. Now here's the center right here. This is, I don't know, home. It's home. Now my direction, if I have, let's talk about our speed. Not our speed, but our distance. Our distance from home, if I'm right here, our distance from home is what? 3 units? Are we good with that? 3 units?
Yeah.
Okay, positive 3 units. What if I'm over here?
Negative 3 units.
Yep, that's the difference between distance and displacement. Displacement is an example of a vector. A vector is what? There's 2 parts to a vector. It is magnitude and direction. Yep, magnitude and direction. All right, so we are not doing vectors at all in this class. So all that fun stuff, you don't need to know. Okay, so today our main idea. Well, first of all, the assignment that is due today is 2.6. And the big idea is rate of change and tangent lines. And tangent lines. So we do know Isaac Newton. So we're looking at almost like 300 years ago, right? Probably 250, 260, something like that years ago. Now, if I have some type of graph right here, and I want to find, let's say that this point right here, let's say that this point right here, let's do this differently. I'm going to draw this again. And we're going to say that I have some point right here. This is my X subset 1 and Y subset 1 versus this point up here, X subset 2, Y subset 2. And I want to find the average rate of change between these 2 points, or the slope between these 2 points. What I'm going to do I have the math to find that?
Yeah.
All right. Well, what is the math if I want to find that the average rate of change from those 2 points, Thomas?
Y subset 2 minus Y subset 1 divided by X subset 2 minus X subset 1.
So you're literally calculating, you're literally calculating slope, right? You're saying, because slope is defined, Slope is, I'm gonna actually write it underneath. Slope is defined by rise over run. And the rise, that's just the difference between your y values. And the run, that's just the difference between your x values. And so that's what Thomas said. So we could calculate the average rate of change from those 2 points by just finding the difference between our y values over the difference between our x values. But the average rate of change is not super helpful if I'm trying to find this perfect balance between, you know, the Earth falling into the sun or the velocity shooting Earth out into space, having that perfect balance. So I have to find the instantaneous rate of change. This is where calculus, this is the pinnacle moment when calculus becomes important. How do I find the instantaneous rate of change? This is where calculus, this is why calculus is invented. How do I find that instantaneous rate of change for a particular point? How do I find the instantaneous rate of change at a point? Question mark. Brandon, you have a question?
I have like theory.
You have a theory. Okay, let's hear your theory.
So would it be, you take the limit of the slope as the slope approaches that point?
Yes.
You just basically get closer and closer to that point. And basically you're taking the limit of the slope.
And that was, yep, that was and that new slope, when those 2 points, we'll get to that, but that new slope is called a tangent line. Now the line we have right here is actually called a secant line. This line here where we go through these 2 points, this is called a secant line. This is called, anytime you, like if I have a circle like this and I draw a line like this, that's called a secant line. This is called a secant line. Now, if I have a circle and I go through, or just a curve of any type, and I go and I just barely touch that 1 point, then we call this, bless you, we call this a tangent line. And it actually is related. I'm not going to get into why you have to do an exploration of trigonometry in general, but that tangent line and that idea of opposite over adjacent, they are intimately connected. We're really talking about the same thing, but from a different perspective. So let's look at, this is literally connected to the opposite over adjacent, but I'm not going to get into that. Just think of, for our definition of a tangent line, I'm going to refer, so a tangent line is a line, I'm going to zoom in a little bit more so I can write better, that goes through 2 points on a curve that are infinitely close to each other. Now, the reason I'm going to say 2 points that are infinitely close to each other is I want to rule out the possibility. This is what I want to say. If I have some curve like this, I want to rule out this possibility here. I'm tempted to say a tangent line only goes through a curve at 1 point. Well, if I say a tangent line goes through a curve at only 1 point, then this is true. But is that really a tangent line?
No.
No. So I'm going to rule that out. Yeah, I'm going to rule that out as a possibility by saying that a tangent line is a line that goes through 2 points on a curve, 2 points that are infinitely close to each other. So if the 2 points are infinitely close to each other, then the only possibility would be something like this, or like this, or like this, right? How many tangent lines does a curve have? Infinite amount. There's an infinite amount. Okay, so but that's not the point of how many tangent lines there are. The point is I need to figure out the instantaneous rate of change. So I know this is not what Bryn said, but I'm going to say this anyway. I'm going to bring this up. I'm going to say, let's say, what if I'm going to use that? Can I just grab that? I'll just have to redraw it. I'll just have to redraw it. So I have my curve, and let's say that this point right here is, I don't know, 1, 2, 3, 3 over, and 1, 2, 3, 4, 4 up. And I want to find that instantaneous rate of change through that point there. What's that called? A line that goes through 2 points that are infinitely close to each other? It's called a tangent line. Everybody, a tangent line.
Tangent line.
Okay. What is a tangent line?
The line that goes through 2 points that are infinitely close to each other.
Cool. All right, so I'm trying to find the tangent line for this curve right here, which is really my slope at that point. It's my slope at that point. Why can't, if I'm trying to find that instantaneous rate of change for at that particular point, why can't I just plug in the same point twice? So 4 minus 4 over 3 minus 3.
Indeterminate form.
It's an indeterminate form. Indeterminate forms sound suspiciously like a limit problem. Does that feel like a limit problem?
Definitely.
Yes, it's
Okay, so let's use our equation where we have this. Let's call this specifically. Let's call this function here. Let's call it f of x. We're going to call this f of x. So we're going to do this again. So how many times do I have to draw this? My word. I should have just cut and pasted, but I've learned my lesson. So I'm going to do this again. We're going to call this curve f of x. Actually, I'm going to move it over here. This is my f of x curve. Now, let's consider that we have some point, some value of x. And if we have some value of x, then if we have some point here, the corresponding y value would be what? That would be f of x. Why? Because isn't that what we do to find our y? If I take this 3 value, don't I plug that into my function to find the 4 value, the y value? Okay, so that's what we do. We just take that x value and plug it in. Now we have some other point. We're going to draw our, what's this one called? It's not a tangent line, it's called a secant line. And we have some other point here of, let's say, this distance here is h. So this x value here would be what?
X plus h.
X plus h. So we have our x plus the h value gives us x plus h. What is the corresponding y value for x plus h?
F of x plus h.
F of x plus h. F of x plus h. How did I get f of x plus h? Well, we plugged it in, right? Because that's how we find our corresponding y value. Okay, this part's really important. What we're trying to do, what did we do up here? What's our y subset 1 minus y subset 2 over x subset 1 minus x subset 2?
So,
Now, what is that in this case? What are our 2 points?
it would be, well, someone else.
Thomas.
X comma x comma f of x and x is h comma f of x. So it'll be the points. Will be,
So our points, the points here, this point right here is x plus h comma f of x plus h, okay? And this point right here is x comma f of x.
yes.
So using our equation for our average rate of change of y subset 2 minus y subset 1 over x subset 2 minus x subset 1, we get what?
F of x plus h
F of x plus h
minus f of x
minus f of x
divided by
h
plus x minus
x plus, let's not skip a step, x
h
plus h
minus x.
minus x. That gives us this slope for the secant line. But I don't want the secant line. I want that instantaneous rate of change.
So you make H small.
Wait. Let's get to that. Now, Thomas said something about this. He was skipping a step down here. How can we, what step was he skipping? Where can we go from here?
Simplification.
Simplify to what?
H.
Hey, yeah, x minus x is gone, so we're left with h. So I'm left with f of x plus h minus f of x over h. Okay, now because this is an indeterminate form where this value here is going to get closer and closer and closer to this value here, so I have what is called a tangent line. I want this point right here to get closer and closer and closer and closer to this point right here. So we have a tangent line. Oops, I didn't do a tangent line there. So what is my limit? My limit is what? What needs to go to 0?
H.
H needs to go to 0. This value here, this distance right here needs to go to 0, correct? Okay, now you're following? Are you good? Okay, so I want that value to go to 0. So I'm going to write this then as the limit as h approaches 0 of this f of x plus h minus f of x over h. This discovery created calculus. That discovery created calculus. That was the first step to calculus coming into existence. Whoa, this is such a powerful moment for Isaac Newton that he's able to calculate the instantaneous rate of change. All right, so we're going to do it. We're going to do it. Okay, is everybody caught up? What's the important part from all this mess? Out of all of this stuff that Mr. Hall talked about, all this stuff, what's the most important thing?
Part you put in the dry box.
Yeah, right here. That's the most important part right here. That limit, that discovery right here created calculus. Right there. Wow. Look at it. Look at it. Marvel over it. Wow.
Yeah, Mr. Hall.
All right. Well, no, it's really cool though. I'm sorry, Bryn, but it's real. This is a,
Letting you know.
okay, but calculus wouldn't exist without this.
I know.
Okay. All right. So now we have, so let's do this. We have y equals, I'm gonna keep it easy. Excuse me. I have y equals x squared. What kind of function is this? What function family does it belong to? Linear, exponential, quadratic, cubic, quartic. What is it?
Quadratic.
It's quadratic. So it's going to look like something like this. How many instantaneous rate of changes are there? Infinite. How many tangent lines can I draw?
Infinite.
Infinite. I can draw one here. 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 There are infinite tangent lines here. So my equation, when I come up with an equation for this, shouldn't I still have x in it? Yeah, because there's infinite solutions. I can figure out what the slope is at 0. Any guesses what the slope is when x is 0? Yeah, at 0. Yep. But I can calculate the slope when x is 1 or when x is 2 or when x is 3 or when it's -1, -2, -3, and so forth. I need to write an equation for those infinite slopes. How do I write an equation? How do I write an equation for those infinite slopes?
Using that one.
Using that equation. All right, so let's do it. What if, let's just change this to f of x, if that's easier to understand. So
Take the Y, just, I can still see the line.
Hickey.
Yes.
I'm kidding. I'm picky too. All right, so here we go. We have f of x. Yeah, especially if something's bothering you with my writing, then just let me know. I'll be glad to fix it. All right, so let's rewrite this equation. What is f of x plus h? How do we, wait, Thomas, I know you know, but this is a connection that some students have a difficult time having. If I have f of x equals 2x plus 3, and I want to find f of 5, how do I find it? Yep, so how do I find f of x plus h? We do the same thing. We do the same thing. We just plug it in, right? So if my equation is over here, then f of x plus h is what? Thomas, now you can say it.
Oh, it's x plus h squared.
Nice. Are we good with that step? This piece here is this. Is that confusing? Okay. Because what we're, okay, let's say that I have f of x equals x squared, and I want to find f of 2. How do I do it? Yeah. What if I want to find, so so now I want to find f.
Is that they're using x in 2 different ways.
It's still something you have to get used to.
It's
So-
just that it's meaning 2 different things at the same time.
It does mean 2 different things. I agree.
Not honestly.
It's something we have to get used to. So so what does this become? Yep. So Bryn's saying, Mr. Hall, why don't you write it this way, where we have f of a plus h? Does that make more sense why this would become a plus h squared?
Yeah, it's just when x means 2 different things, then it's just like you're not, that just doesn't work.
It's confusing. I get it. It's confusing, but it's,
I know what it means, it's just like, it affects like my math.
it's still something you have to get used to. It's still something you have to get used to. It's 2 different x's. That's why we use y subset x. We use y subset 2 and y subset 1 to distinguish the difference between the two. Yeah. Okay. So the question, Kana, is why is this x plus h squared? Why is this x plus h squared?
Because if f of x is x squared, and then x plus h, and then square it, right?
Yep. So Kana, what's this part here?
X squared.
Yeah, that's just x squared. That's just that part's easy. That's just x squared. It gives us it right here. So we have minus x squared over h. Now I'm missing something really important. What did I miss? Yeah, I have to have the limit. This is not the same thing as this idea that Isaac Newton discovered. We need to have this piece, the limit as h approaches 0. Okay. All right, now what? All that fun stuff. Remember the different tools for finding limits. What was the suggestion? Expand. This one would be expand. Remember that one? Remember that option, expand? Okay, so I'm going to expand this x plus h squared, which becomes x squared plus h squared?
No.
No.
No. What do I have to do?
X plus 2x8 or 8x.
That gives me, I'm going to do this. I'm not going to skip a step. I'm going to do x plus h times x plus h minus x squared all over h. This is still the limit. I'm still trying to find the limit of this. Okay. Now what? Now we can distribute. If we distribute, what do we get?
X squared plus two X.
You want to skip a step.
Okay.
That's
Plus
a,
HX plus HX if you are going to be picky.
hey, wait, you're picky with me, so there you go. Okay,
And then finally plus X squared.
all right, okay. Are we good with that? Yes, no, maybe so? Okay, now what?
Simplify it out.
What can I simplify at the top?
You can cancel the x squared.
I can cancel out these x squareds. Good. This and this goes away, all right? Leaving me with the limit as h approaches 0 of 2xh plus h squared over h, okay?
Factor out H.
Factor out the h. So that gives me the limit as h approaches 0 of h times 2x plus h over h. Is that all right? Okay, now what?
Then you can cancel out the,
Cancel those out.
and leave a one at the bottom.
And so that,
And finally, it's not gonna be an indeterminate form when you plug in zero.
which gives me what then?
It would just be two X plus H.
Well, you said you could plug into 0.
So basically now it's finally, given that it's not gonna be a zero on the bottom, it's not gonna be, it's not gonna be the problem child once we plug in zero.
Which gives me what?
Say two X, it's two X.
That's 2x, good. What did I find? What's the relevance of that?
Now you know the instantaneous rate change for any part on travel.
I know that, yeah, what this calculated is the instantaneous rate of change for any x value on the parabola. What did this give me? Kano, what did this give me? What's the relevance of this? Why is 2x important?
The instantaneous rate of change.
Where?
At X squared.
Where did it give me the instantaneous rate of change? For any x value on the domain of this curve, of the parabola.
And is it in infinite domain?
Yeah. Is it a parabola? Isn't the domain infinite? There's no interruptions. So what is the slope when x is 0?
Zero.
If I plug in 0, okay, now what do I get? What's the instantaneous rate of change when x is 1?
Two.
Kana,
Oh, sorry, two.
what's the instantaneous rate of change when x is 2?
Four.
Yep. What's the instantaneous rate of change when x is -1?
Negative zero.
What's the instantaneous rate of change of when x is -2?
Negative four.
-4. Does everybody see that? Okay. Logan, what's the relevance of this? I took this f of x equals x squared, and I went through this process, this awesome discovery from Isaac Newton, and I calculated this x squared. What's the relevance of this x squared?
And it's not X squared, it's two X.
Oh, did I say it wrong? All right,
Instead of X squared.
I apologize. So we discovered this 2x. What relevance is the 2x? It tells me what? For any x value on the graph,
For the relevancy on the graph, at any point that is probably the x value, like one x. Or the x value, any x value.
it tells me the instantaneous rate of change, right? Tells me the instantaneous, that was the whole point of what Isaac Newton was trying to discover, is that what happens, what is the change at an instantaneous point? All right, so let's do another one.
Stop moving around so much, so that,
Oh, were you still copying?
yes.
I apologize. Is that better?
Just up, no. Thanks.
Everybody good? Yes, no, maybe so? Not quite? Okay. Awesome. Let's say, here's another question. At what value of x is the slope 8? Now, what value for x is the slope 8, or the tangent line, if you prefer, the slope of the tangent line? Jillian? It's 4. Yep. So our equation then, this is for any slope, our equation is 2x. And so we're going to take that 8 value, plug it in, and then that we just solve for x. We divide both sides by 2. That gives us that our x value is 4. Are we good with that?
Yeah.
Okay. Let's do a more difficult one. I have y equals 1 over x. What kind of function family does that belong to? Bryn?
Rational.
It's rational. We have a polynomial divided by a polynomial. This is a rational function. So one of the characteristics of a rational function is asymptotes. So we end up with something that looks like this. Is this more or less what you remember this looking like? Okay, I want to find our instantaneous rate of change function for this. What is also called the derivative equation, or the derivative function. Find the derivative of
All the time.
this function. What does derivative mean?
It's change in change.
It's my instantaneous rate of change function. When I talk about a derivative, I'm talking about that function that we figured out using that limit. Adam, what is a derivative? Yeah, it's that equation that gives us the rate of change, that instantaneous rate of change. What is the word, Mariah? What is the word in calculus for the equation that gives us the instantaneous rate of change? Yeah, it's called a derivative. It's called a derivative. Gaia? Gaia, what is a derivative? The instantaneous rate of change. It gives us the equation for the instantaneous rate of change. I agree. Jacob, what is that word in calculus that refers to the equation that gives us the instantaneous rate of change? It's called a derivative. Yep, it's called a derivative. Ethan, where's Ethan? Ethan, what's a derivative?
I know this, but I don't. Hold on.
Jack, what's a derivative?
It's the equation that gives us the instantaneous rate of change.
It's the equation that gives us the instantaneous rate of change. Ethan, what is that word in calculus for the equation that gives us the instantaneous rate of change? It's called a derivative. Yeah, it's called a derivative. All right, let's find the derivative. Let's find the derivative for this. Thomas, you already have it.
Well, I do, but I want, there's another way to know something with it.
I don't want you to teach that way yet. No shortcuts yet. We have to earn it. Do you think that Isaac Newton started out with the shortcuts?
No,
Do you know how we got the shortcuts?
by doing it.
By doing this over and over and over again and noticing a pattern.
Yeah.
Okay. Where did we get?
Yeah.
Where-
If you don't recognize where you got the pattern from, then how can you explain how you got the pattern?
True.
We can't think. Do you know about what is it called? Is it called the ancient astronaut theory? Where all of the knowledge we know was delivered to us by aliens, that humans didn't learn anything.
You know, I've heard it somewhere.
That's just crazy. We can't skip those steps because that makes us start believing that somebody just gave us this knowledge. We have to earn it. So you guys need more time? Too early, maybe? So what's our equation? What's the equation we're going to use? We have to use the equation of the limit as h approaches 0 of f of x plus h. Okay, good. Nice. Okay. So maybe zoom out a little bit so we can see this a little bit better. What is f of x plus h? Jillian, what is f of x plus h? It's 1 over x plus h. Good. Minus? Isn't this just my f of x function? Oh, now Brendan's going to get mad at me. I'll risk it. All right, so my f of x is what?
Yeah, they do it in the same color.
Okay, 1 over x, all over what? I don't want the limit under the line, over h, yeah. All right, this reminds me of one of the tools. What was one of our tools for solving for a limit? Get a common denominator. Remember that one? Get a common denominator. You guys want some think time? Or are you guys stuck? Who wants think time? Raise your hand. Okay, I'm going to give you a little think time. To find that equation. Oh, I forgot what the name of that was. The equation that we're about to find is called what? It's called the derivative. Yep, it's called the derivative. Right? Are you stuck? Do you remember how you add two fractions or subtract? Yep. So our first step should be to multiply this side by 1 in the form of what? X plus, it's h, I'm sorry, it's h over x plus h. And this one over here? X over x, yep, that's the first step. I think it's called ancient alien astronaut theory. Is that what it is? Yeah,
You sound kind of the 17-foot tall goat here.
never heard of that one. Tate, you have a question?
Wouldn't the denominator be, like, the denominator of all of it be h? Why would it be x, the second one?
Over here?
Yeah.
On the very bottom.
Oh,
you did mess up.
Tate, it was because I was being sloppy.
Good job, Dave.
Good job, Tate. Good job. Yeah, I'm certainly not perfect. If I make a mistake, let me know. This was an H. Tate, are you done? Or did you figure out what the derivative was?
Not yet, but
What was your next step? Yeah, this limit as h approaches 0, we can add the numerators, right? Or we can put the numerator together to get x minus x plus h all over x squared plus, I'm gonna leave this as in factored form because sometimes things can cancel out. I'm just gonna leave it in there, hoping that maybe it'll be beneficial somehow later. Right, and then all over h, right? Or h over 1. Any suggestions now? Yes, Thomas?
You distribute the negative.
We distribute the negative, all right, so that's gonna give it me the limit as h approaches 0 of x minus h over x times x plus h. What's the rule when we divide by fractions? Here's a tip.
Keep, change, flip.
Okay, so that'd be 1 over h, okay? Adam, now what? Yeah, what can I do with this? Nice, x minus x, that's gone. So I have this, the limit as h approaches 0 of negative h over x times x plus h times 1 over h. Adam, do you see anything else? So yeah, isn't this called cross simplification where we have h divided by h? Yeah, so I have the limit as h approaches 0 of negative 1 over x times x plus h. Yep. Can I do anything else, Adam, from here? We can, you're right, we can do that, but isn't it also true that we can plug in this 0, or are we violating a rule of math by doing that? If I plug in, well, the biggest problem is getting a 0 in the denominator. If we have something over 0, that's undefined. If I plug in 0, do you see anything that like a mathematical rule that I break? Yeah, it looks like it works. So I don't violate any rules. So that just gives me the limit as h approaches 0. If I plug in that 0, doesn't that just give me negative 1 over x squared? So I get negative 1 over x squared. Does that look right? Okay, what is this, Adam? What is this called? It's called the derivative. Yep. What is the slope? What is the slope? What is the slope when x equals 2? Yeah, negative 1/4. That's my slope, negative 1/4. That's my instantaneous rate of change. When x equals 2, my instantaneous rate of change is negative 1/4, which means that the graph from left to right, is it going up or down when x is 2? It's going down. My slope is negative, so that the slope is, should be decreasing. Let's find another one. Okay, find the derivative. I'm gonna go closer. Am I going too fast? Bryn, are you still writing?
No, actually not.
Anybody else still writing? Okay, here's the next one. I want to write an equation. Write an equation for the tangent line through to 4 of f of x equals x squared. Write an equation for the tangent line through 2, 4 of f of x equals x squared. If I'm going to write an equation, is the equation going to be linear, exponential, quadratic? What's the equation going to be? The equation of the tangent, or for the tangent line. It's linear, so I'm going to use this y equals mx plus b. How do I find this m?
Derivative.
We do the derivative. We already figured out the derivative, right? What is our derivative? 2x. So what's my slope? What would my slope be? What's my slope? How did you get 4? I agree with you. It is 4. How did you get 4? How did you get a slope of 4? Yeah, let's plug in this 2. This is an x value. Let's plug in that x value here. That gives us that our slope is going to be 4. So I have our slope is going to be 2 times 2, which is 4. So I get 4 here. So I have y equals 4x plus b. What am I missing? How do I get a b value? Thomas.
You plug in a point.
Yeah, we have a point right here. Let's plug it in. What's my y?
4.
The y is 4. This is my y value. This is my x value. I'm going to plug those in so that I get 4 equals 4 times 2 plus b. So what's b? What is it?
-4.
-4, yeah. So my equation then is what? Y equals 4x minus 4. Should we graph it? Should we see? So we see if let's see if this is true. Do you guys need to copy this first? Nate, you're good? Okay. So I'm going to go to Desmos. Right, I have my f of x equals x squared. And then my other equation was y equals 4x minus 4. That gave us this blue line here. How did we do? Is this a tangent line?
Yeah.
Yes.
What defines it as a tangent line?
That's just a
it passes through 2 points that are infinitely close to each other. Does it go through the point that we had identified earlier? Okay. And then how do we know whether it has a slope if our, well, I guess we can just see that it's 4, I guess. But yeah, there you go. What's the most confusing part of this? What if I have y equals x? Let's do 3. Let's do 2x cubed. I want to find the derivative. Find the derivative. What happens next time you come to class on Friday? Pre-test. Pre-test on limits. Any guesses what chapter 3 is about?
More of this.
Derivatives. Chapter 4, derivatives. Chapter 5, derivatives. And then we get into antiderivatives. Remember how you're always, yeah, integrals. Do you know how you're always, this is a common theme in math. You're given some type of operation like addition, followed by the inverse, which would be subtraction. And then you're introduced to something like multiplication, followed by the inverse, which was, so guess what direction we're going in calculus? We're going the antiderivative. Yeah, we don't call it an inverse derivative, even though it sort of is. There's something that's lost along the way, but we'll get into that later. It's basically an inverse.
The first thing I thought of was the inverse of the derivative. It's funny because it's some operations.
There's some really cool stuff. There's some really cool stuff in physics with derivatives and integrals. I'll give you a hint. This is sort of a cool idea, the direction we're going. Let's say that this is time and this is distance. And what would the slope of a time versus distance equation give you?
Hi, do you want a Highland soccer?
Yes, please. Can you just put it on the desk over there? Thank you. What would, if I have a time versus distance equation, what would the slope, what units would the slope be in? Velocity. Do you get it? Do you guys agree with that? That the rise over run would be, the rise is distance over the run, which is time. Distance over time is what? Like miles per hour? It's velocity. If you're doing, all right, so what if I have an equation where I have, this is the velocity. We're saying that this is going to be, this is time, this is the velocity, and I want to go back to distance. You would have to use the antiderivative to do that. If the derivative is the slope, then the antiderivative brings you back to the equation. So these are intimately connected. In fact, it's sort of weird that it turns out this is sort of a crazy idea. This is a really crazy idea. If I have something like this, I have time, and this is velocity. And I have, let's say that this is 50 miles per hour, just keeping it simple. And this is, say, let's do 6 hours, 6 hours. How far did I travel in 6 hours if at a constant velocity of 50? 50 miles per hour. How much?
300.
300 miles, 300 miles. Isn't that my base of 6 times the height of 50, which is area?
Yeah.
The inverse of a derivative is area. What? That's some really cool. So it turns out to be the area under the curve. That is so cool. That's so cool. The inverse of an instantaneous rate of change is the area underneath. That's crazy. That's some crazy math, but it's true. It is true. Okay. Yeah, but that's an important tangent. It was a tangent about tangents. Right, so let's grab this. Sorry? A tangent about derivatives, yeah. Yeah, derivative. Yeah, it's a huge circle. It's a huge circle. All right. More time?
I do need more time.
All right. Well, I didn't help that Mr. Hall was talking, right? What's my equation?
Limit at h equals 0 of f of x plus h minus f of x.
Yep. What is f of x plus h? Okay, what is f of x? I'm gonna cheat. Does anybody remember how to do the, what is it called? The binomial expansion
I'm pretty sure.
using Pascal's triangle?
I do.
You
But
do?
I'm not sure if I learned it in this class or if it was just something that my mom showed me because it was fun.
It actually was, I did teach this in secondary math 2.
In secondary math too.
Oh, sorry, secondary math 3.
Yeah, because if it wasn't secondary math too, then I wouldn't have got.
Yep.
Yeah. But it would just be.
X
X cubed.
plus
Plus
Plus.
x squared.
x squared.
H, and that's 2x squared H.
Good, because of Pascal's triangle, 1, 1, 1, 1, 2, 1. We're using 1, 1, 3, 3, 1. So wouldn't there be,
Yeah.
isn't there 3 of those?
Right,
Okay, there's 3 of those.
3,
Plus,
plus
H
3
squared.
x H squared plus x.
x, h cubed.
H cubed, yeah, yeah.
Okay.
All over it.
And oh, what about this part?
Minus 2x cubed, because that's just the simple part.
Okay, all over h. I forgot limit. Limit as h approaches 0. Gosh. You could certainly write x plus h times x plus h plus x plus h and then expand all that mess, but it's a headache. Can I eliminate anything here?
X cubed.
Yeah, these values here are going to be eliminated. Oops, wrong tool. This value here and this value here. I still need to distribute the 2 here, here, and here, right? So I have the limit as h approaches 0 of 3x squared h plus 3. Oh, I'm not distributing the 2. 6x squared h plus 6x h squared plus 2h cubed. Does that look right? Is anybody lost? Where did you get something different here?
Yeah.
Okay, so let's write it out and do it the other way. So the other way is that I could have rewritten this as this piece here could be rewritten as x plus h times x plus h times x plus h. And then we distribute here and here, that gives us x squared plus 2xh plus h squared. Are you okay if I skip a step?
Yeah, I just distributed the two to one of them as well.
Oh, this is all, there's a 2 out. Oh, where did you just to any of them?
I did.
Do you mind if I just do it
The same, and then I had two x plus,
on the last one?
yeah.
Okay, let's do that. So we still have that 2 there. So this part here, you had 2x plus 2h. Okay, now I'm going to distribute. I need to distribute all of this here, here, and here. That's 2x cubed plus 4x times h plus 2h squared. Does that look right? Yes?
Yeah.
Okay, now let's distribute the 2h. 2h times x squared is? 2x squared h, okay? Distribute here to get 2h times 2x h would give me what? 4x h squared? Is that right?
Yeah.
I wanted to line everything up, but I see I don't have enough room to do that. I'll just write it over here. It doesn't feel very organized though. 4. It's 4. 4x h squared. And what about 4? No, I don't think I wrote that right. No, 4x h squared. Is that right? If I distribute this to here. 4x h squared, yes?
Yeah.
Okay, and then distribute here.
Yeah.
It gives me plus 2h cubed. So that gives me 2x cubed plus, that takes care of this one here. And then I have plus 2x squared h. We should be combining these with something else. And I don't see that let me do this again. Okay, I'm gonna just start over. I'm gonna distribute this 2x. So I have 2x cubed plus 4x squared h plus 2x h squared. Now I'm going to distribute the 2h times x squared, 2x squared h plus 4xh, there we go, 4xh squared plus h cubed. That looks better. And then when we combine these, we get 2. Yes, Thomas.
Yeah, this was, is 2h cubed.
It's 2.
2h cubed.
2. Okay. And then we have 6xh squared plus 2h cubed. And then these, those canceled out. And so what I'm missing is the 3 here, right? Yeah, I'm missing that. That should have been cubed. So this part here canceled out up here. Then we have this here, and this here. Yeah, it looks right. Even if you distribute, you still get it right. All right, so all of that is over h. Okay, now what? Yes, Thomas,
then you factor out an H,
factor out an H.
factor.
So that gives me the limit as H approaches 0 of H times 6x squared plus 6xh plus 2h squared over h. Does that look right? Okay, now what?
Cancellation.
Cancel out the h. Am I going too fast? Okay, I cancel out the h. What's left over is the limit as h approaches 0 of 6x squared plus 6xh plus 2h squared. Now what? Plug in the 0, and that gives me what? My derivative function is what? 2x squared. That's it. Nice. Are you guys seeing? Let me move this up to the top. What we found so far let's see if we see a pattern. Okay. I started with, so here's my function. And then the derivative. And I started with x squared, and my derivative was what? 2x. Then with this last one, I have 2x cubed, and I got 6x squared. And then we even had a 1 over x, which is really, using one of our laws of exponents, is really just x to the power of -1. And what did we get? 1 over x squared? -1, which means that I have negative x to the power of -2. Is that right? Did we do any other ones? Is that it? I don't know if you guys see a pattern yet. I see a pattern. What do we do to the exponent?
Put it on a trampoline.
We move it to the front. What do we do to the old x, or what happens to the exponent?
Oh, you must have done it.
Okay, we move the exponent to the front, but what happens to the exponent?
Because it subtracts by 1.
It subtracts by 1. So if I have a times x to the power of n, then the derivative is going to be what?
A
an
x
x
power n minus 1.
n minus 1. That is the pattern that had to be discovered over and over and over. So that had to be discovered by doing the problem the old way over and over and over again. This is called, does anybody know what this is called?
Power rules.
It is called the power rule. Aliens did not deliver this knowledge to us. Mathematicians had to painstakingly discover this by doing this the other way with the limits over and over and over and over again. Here's another really cool discovery. What if you have multiple terms? What if I have something like this? I have y equals 3x squared plus 2x minus 7.
Yeah.
We can what? Yeah, we can do the power rule to each term individually, and it'll still give us the derivative function. So my derivative, in fact, I'm going to start using derivative function notation. I'm going to use, if I'm going to find the derivative of y, I'm going to use y, and then I'm going to use a little, an apostrophe. It means the derivative. There's actually a number of different ways to write the derivative. Another way to write the derivative would be dy dx, which looks suspiciously like what? The change rule. That's our change rule of the difference between our y's over the difference between our x's. Okay. Yes, sir.
So
Yeah, what,
They don't follow the power rule, do they?
yeah, let's do a constant. Okay, so Thomas is making the argument that a constant doesn't follow the power rule. Now let's consider what this would look like individually. I have y equals -7, which is just a horizontal line. What is the slope of a horizontal line?
Zero.
It's 0. All right, so the answer should be 0. Now you said it doesn't follow the power rule. Let's make sure. This is x to the power of what? If it's a constant, what?
One. Zero.
0. Okay, let's follow the rule. The rule would say to do what to this? -7 times what?
Oh, that's not the zero, I see.
0 times x to the power of -1. But since I'm multiplying by 0, it's all gone.
Yeah, cool.
It still follows the power rule.
Thank you.
Okay, so let's find what is the, using the power rule for this function here, what's the derivative? Kana, what's the derivative?
Wait, are we talking about that one?
This one right here.
Oh, the whole thing?
Instead of plugging this into the, if I did this the old way, this would be the limit as h approaches 0 of 3 times x plus h squared plus 2 times x plus h minus 7 minus 3x squared plus 2x minus 7 all over h. Or we can use the power rule. Do you agree that this would be a headache?
Yeah. I don't know.
Okay, so how would we do this by using the power rule?
So for the first one, we do 2 times 3x to the first,
2 times 3, yeah, which is what?
which is 6x,
It's just 6x, okay?
and then plus 2,
Uh-huh.
and then there's nothing.
Yep, there you go.